Welcome to Electronics Excel. So we are discussing about the previous year question series of digital signal processing. Okay, 2022-23. So in the last lectures, we have seen the short type questions. Basically, we have discussed the 10 number of short type questions, each having 2 marks. Then we have discussed about the 6 number of 6 mark questions. Okay. So remaining 6 marks questions we will discuss in this lecture. Okay. So the first question is that list the all the properties of Z transform. Okay. So you have to list all the properties of Z transform. So first property is the linearity property. So the if the Z transform of x1 of n is your x1 of z and x2 of n, the Z transform is x2 of z. Okay. Then x1 of n, which is a1 x1 of n plus a2 x2 of n, whose z transform is x of z, which is given by a1 x1 of z plus a2 x2 of z. So this property is called the linearity property. Okay. Next, a1 and a2 are constants. Okay. Then time shifting property. So if x1 x of n, the z transform is x of z. So x of n minus k. So it is shifted by k units in time. So that would be z transport would be z to the power minus k into x of z. Okay. So this is the time shifting property. Next is the scaling in z domain. Okay. So if x of n, the z transform is x of z, then a to the power of n x of n, whose z transform is x of a inverse z. Okay. Similarly, time reversal property, if x of n, the z transform is x of z, then x of minus n. Okay, so whose z transform will be x of z inverse. Okay. Then differentiation in z domain. So if x of n, the z transform is x of z, n into x of n, the z transform is your minus z into d by dz of x of z. So this is the differentiation in z domain. Okay. So then convolution of two sequences. If x1 of n, the z transform is x1 of z, and x2 of n, the z transform is x2 of z, then x of n, which is x1 of n, convolve with x2 of n, whose z transform is x of z, that will be x1 of z multiplied with x2 of z. Okay. Then correlations of two sequences. Similarly, if x1 of n, the z transform is x1 of z, okay, then x2 of n, the z transform is x2 of z, then which correlation is this one? This is the formula for finding out the correlation. This is the cross correlations. So whose z transform will be that will be the x1 of z into x2 of z inverse. Okay. So this is the these are the properties of Z transform. Okay. So basically, this question asks about the list all the properties of Z transform. Okay. Next is here, the second question is that the explain the inverse modeling using the adaptive FIR filter. Okay. So this is the block diagram of a adaptive filter. Okay. So in this case, you can see the inverse modeling is used technique used to recover the original input signal from the output, okay, of an unknown system. Okay. So this is our inverse modeling. So consider an unknown system which transfer function is h of z. Okay. So this is the unknown system which transfer function is h of z, which is the input. It takes the input x of n and the output is your d of n. Okay. So the adaptive FIR filter W of Z is connected after the system. This is the adaptive FIR filter, which is the transfer function is that W of Z, which is connected after the means unknown system. Okay. And Dn, it takes the Dn is the input. It will take the Dn as input and it will provide the output Y of n. Okay. Next is your input passes to the unknown system, that is x of n. Okay. And d of n, so d what is the output of this unknown system? So d of n is x of n convolved with h of n. Okay. So adaptive filter then takes d of n. Okay. So then it will provide the output. So that will be y of n equal to summation of k equal to 0 to m minus 1 w of k into d of n minus k. This is the output of a adaptive FIR filter. So y of n basically it is that k equal to 0, 1, you can put over here and you will get these equations. Okay. So the error, the signal that is y of n is compared with the original signal, okay, to produce and generate an error. The output is y of n compared with the original signal that is x of n. So error signal equal to x of n minus of y of n. Okay. So this is the minus of y, this minus of y of n. Okay. So it's the error signal, this is the x of n, this is y of n. So that error signal u of n equal to x of n, that is the minus of y of n. Okay. This is the error signal. Okay. The error signal should be as minimum as possible actually. The error signal used to update the filter coefficients using an adaptive algorithm, most probably LMS algorithm, this means square. The filter adjusts itself to minimize the error. Okay. The main aim is to minimize this error. Okay. So when the error becomes 0 or minimum, this xn is equal to y of n. Okay. So this is how the inverse modeling used in case of adaptive FIR filter. Therefore, the adaptive FIR filter acts as in the inverse of an unknown system. Okay. Next is here. For the analog system response, S of x equal to b upon s by a. So we have to prove that h of z equal to this one. Okay. So so h of s equal to given, s domain value is given. So we have to prove that h of z. Okay. So let us see that in bilinear transformation, it is obtained by the trapezoidal formula for numerical integrations. Okay. So we can have the trapezoidal formula. Okay. So this is we can done by using the means IR filter design using the bilinear transformations. So let the system functions that analog filter would be h of s equal to b upon s by a. Okay. So now h of s, which is y of s divided by x of s equal to b upon s plus a. Okay. So now you can cross multiply this. So s into h y of s plus a into that is y of s equal to b into x of s. So by taking the inverse Laplace transformation, so that would be dy of t by dt plus a into y of t equal to b into x of t. Okay. Now integrating this between the limit nt minus t to and n of t. Okay. Let us integrate this. So nt minus t into nt. So d of y of t dt into dt. Okay. Then integrating a is a constant taken outside. Y of t dt plus b is a constant that is taken outside. So and this is x of t dt. Okay. So integrating this between the limit nt minus t to n of t, n of nt. Okay. Now this is the means integration that will be uh, and T over T. This is we have written that in the previous slide also. So by using the trapezoidal rule of numerical, this is the trapezoidal rule of numerical integration. So if we integrate from nt minus t to nt, a of t dt, that will be t by 2 a into nt plus a into nt minus t. Let us apply this formula. So we can apply this formula over here. So in case we can see this dt will be cancelled out. Okay. So it will be y of t. Okay. So y of t only. Okay. So that will be y of t. So y of t. Okay. So if we put y of t, the limit is from nt minus t to nt. Okay. Nt. So that will be y of nt minus of that is y of nt minus t. Okay. So nt minus t plus you can put this formula. This is the formula. So in this is y, so we can replace that is by y. So this is this integration. So a t dt, that is y t dt. Okay. So it will say that will be a is a constant. So a into t by 2. So into t by 2. So y of nt plus y of nt minus t. So into a t by 2. Okay. A t by 2 is multiplied with a and t plus a into this one. Okay. Similarly, this integration by using the trapezoidal numerical integration, it will be bt by 2, so x of nt plus bt by 2 into x of nt minus t. Okay. So now with y of n equal to y of nt and x of n equal to x of nt, we get this one. Okay. So y of n minus y of n plus 2 plus at by 2 y of n plus this one. So is equal to bt by 2 x of n plus bt by 2 x of n minus 1. Okay. Now if we put the z transform, so that will be we will taking the z transform. So what is the that actually what is the equation? So y of n, so y of n minus of y of n minus 1 plus a t by 2, that is y of n plus y of n minus 1, that is a t by 2, so it's equal to b t by 2 x of n plus b t by 2 x of n minus 1. So by taking the, you can take the Z transform. So y of z, the Z transform is y of n, the Z transform is y of z. Similarly, y of n minus 1 means z to the power y minus 1 y of z. Okay. Similarly, this one is of a t by 2, so that will be y of z. Okay. Similarly, z to the minus 1. Okay, this z transform. So that will be a t by 2. Similarly, this b t by 2, so that will be b t by 2 x of z plus bt by 2 z to the power minus 1 x of z. Okay, so this is the z transform. Okay, uh, at by 2 z to the power minus 1. Okay, that is the this will be the z transform. Okay. So now, so we can get this. So take yz common over here. Yz if we take common. Okay, so it will be 1 plus at by 2 y of z. Okay, in this third term and first term you can take common y of z. Similarly, this is z, y of z you can take in the z inverse term. So this is the one z inverse term. Okay, so this is your the z inverse term. There is a z, this one another z inverse term. So you can take common. Okay, so this is actually y of z. Okay, so z inverse means a t by 2. This is y of z. Okay, so you can this term and this first this z inverse term you can take common. Okay, so we can get this one. So y of z in z inverse this one. Similarly, this x of z you can take common bt by 2 x of z, that will be 1 plus z inverse x of z. Okay. So now y of z by x of z you can get this one. Okay. Now bt by 2 1 plus z inverse, you can simplify this, you can get this one. So now dividing the numerator and denominator by t by 2 1 plus z inverse. Okay. So you can get this one. Okay. So now comparing this original signals, the mapping will be s equal to 2 by t 1 minus z inverse plus 1 plus z inverse. So we have taken b by s plus a. Okay. H of s equal to b by s plus a. So this is s, this whole term is your s. Okay. So the mapping from s plane to z plane equal to this one. Okay, in bilinear transformation method. Okay. So next one is your differentiate between impulse invariant and bilinear transformation in the design of IR filters. Okay. So impulse invariant and binary transformation. So impulse invariance we are mapping from all the S domain to the Z domain. So in this case also, so h of n is proportional to the sample impulse response, that is h of a n of t. Okay. So this is the analog domain, this is the digital domain. So Z you can take e to the power of s of t, s into t. Okay. And in binary transformation that we have seen in the previous slide also, so this substitute s with in this equation 2 by t 1 minus z inverse plus divided by 1 plus z inverse into the means analog transfer function, that is s of s. Okay. So next is your, it suffers from impulse invariant method, it suffers from aliasing. Okay. It maps the frequency range from S plane in the range -5 to 5 in the Z plane. Okay. So it suffers from aliasing, but in this case no aliasing, because aliasing means that two bands are overlapped. That is the aliasing. So data will be lost. Okay. So this aliasing, there is no aliasing in case of the bilinear transformation. It will map the S axis to the unit circle of the Z planes. So it is the mapping is linear in case of impulse invariant. Okay. But there is a aliasing that causes the frequency response distortions. In this case, this mapping is non-linear, but it causes the frequency wrapping. Okay. Next one is uh, next point is that it is suitable for band limiter filters such as a low pass filter. Okay, so band limiter means that filter will be band limiter, so no frequency above that band. Okay, so this band limiter filters have the such as low pass filter. This is suitable for low pass filter. It prefers bilinear transfer is preferred for the high pass, band pass, and band reject filters. Okay. Similarly, it maps only the poles, but in case of bilinear transform, it maps both poles and zeros. Impulse invariant method, it is many to one mapping, where the bilinear transform is the one to one mapping. So this is the relationship between the analog and digital frequency, which is linear in case of the impulse invariant method. This is the relationship between the analog and digital frequency, which is non-linear in case of the bilinear transform method. So to prevent the aliasing, the analog filter should be band limited. So in this case, there is no problem of aliasing. So the analog filter need not to be band limited. So these are the difference between the impulse invariant method and bilinear transform method in case of the IR filter design. Okay. Next is the difference between DIT FFT and DIV FFT. So the decimation in time and decimation in frequency. So let us see that. So it is the time domain is decimated in this case, DIT FFT. DIF means the frequency domain is decimated. Similarly, the input samples is n equal to 2 to the m, where m is the integer, which is the number of stages. Okay, the same is in this case also. The input samples are n equal to 2 to the power of m, where m is the number of stages. This is the DIT FFT. The input sequence is shuffled for bit reversal order. Okay, but in case of DIF FFT, the input sequence is natural order. Okay, the number of stages in the butterfly or flow graph equal to m equal to log to n. Here is also same. Okay, m equal to log to n. Each state consists of n by 2 butterfly. Here also each stage consists of n by 2 butterflies. Similarly, in case of DIT F15, the input and outputs of each butterfly are separated by 2 to the power m minus 1 samples. Okay, so here m is the stage index. Similarly, in this DIFFT, the input and output of each butterfly are separated by 2 to the power m minus m samples, okay, where m is the stage index. Okay. So number of complex multiplication equal to n by 2 log to n. Here also the number of complex multiplication is your n by 2 log to n. Complex addition is your n log 2n. Similarly, this is also the complex addition is your n into log 2n. So in case of DITFFT, this is the total factor. So k equal to nt by 2 to m. That is how we calculate. Okay. Similarly, in case of DIFFT, the total factor is this one. Okay. So in the number of sets of the section of the butterfly of each stage is given by the formula equal to this one. Okay. In this case, the sets and section of the butterfly is given by the formula 2 to the power m minus 1. Okay. So ERF, that is the exponential repeat factor. It is 2 to the power m minus m in case of DITFFT. In case of DIFFT, it is 2 to the power m minus n. So exponent repeat means the number of times the exponents repeats. Okay, that is the 2 to the m minus 1 in case of DIFFT. In case of DITFFT, it is 2 to the m minus m. Next one is the input should be in bit reversal order that we have seen, and output should be in the normal order. In case of DIFFT, the input should be in normal order and output will be in the bit reversal order. You can see the each set the total factors are multiple before the add and subtract operations. In this case, the total factors are multiplied after the subtract and add operation. So in case of means DIFFT, you can see it is a plus b into this is omega into the k. This is when we find out the total factor. This is a minus b. So that is the, you can see a minus b or a plus b. You can check. Okay. So this is the total factors. In case of this is after addition or subtraction, it will be means multiply. But it is the before the addition subtraction. It is the, what is the value? So a plus b omega n to the power k. Another one is a minus b. Okay. So after this total factors are multiplied before the add or subtract operation. In this case, but it is the multiplied after the add and subtract or add and subtract operations. Okay. Next one is the value of n should be expressed that is n into equal to 2 to the power of m. The algorithm consists of m stages of computation. This is also the same. Okay. So these are the difference between the DIT and FFT algorithms. Okay. So you can write as many as 6 points. Okay. Because it is a 6 mark questions. Okay. So last one is draw the 8-point DIF FFT structure finding the IDFT of a sequence. Okay. So in case of DIF FFT, the number of input samples is 8, and the input sequence is a natural order. The number of stages of the flow graph equal is the formula. Next is each stage consists of n by 2 butterfly. So input and output are separated by 2 to the power m minus m samples, where m is the stage index. So m equal to 1 for stage 1. So input and outputs are separated by 2 to the power of 3 minus, that will be 4 samples in case of means stage 1. Stage 2 we have the 2 samples, and stage 3 we have the input and outputs of each butterfly means separated by only 1 samples. Similarly, the number of complex multiplication equal to, that is the n equal to 8, so that will be 16. Number of complex addition equal to 8 into log to 8, that will be 32. The total factors are the function of stage is m, that is given by this the formula. For stage 1, the exponents were 0, 1, 2, 3. For stage 2, the exponents are, means these are the k values, okay? 0 and 2. For stage 3, the exponent is 0. Okay? So you can see the number of sets of the section of the butterfly in state. For stage 1, the number of sets and section of the butterfly equal to 1. Similarly, stage 2 it is 2. Stage 3 it is 3. 4. Okay. So exponential repeat factor for stage 1, k 1, and stage 2, that this is the k, means number of times the exponent sequence is repeated. So in stage 1 it is only 1, in stage 2 it is 2, and in stage 3 it is 4. Okay. So let us see the diagram. This is the means this diagram is the flow graph of the 8-point DIF FFT. So you can see over here. So input and outputs, that is the input and outputs are means inputs are taken in the normal order. You can see the inputs are taken in the normal order. The outputs are that is the bit reversal order. Okay, the bit reversal orders. So you can see this means the exponent repeat factor, you can see that is 0, 1, 2, 3. This is the stage 1. Okay, so this is our stage 1, stage 2, and this is a stage 3. Okay, so you can see the input and output of the butterfly, okay, are separated by 4 samples in this stage 1. Similarly, the input and output of butterfly you can see separated by 2 samples. So if we take this butterfly, you can see this is the input, output is this one. So it is separated by 1, 2 samples. There are 2 samples. Similarly, in stage 3, the input and output, you can see this is the input, so corresponding this is the output. Okay, so this it is separated by 1 sample. Okay. So you can see if you take this butterfly, so this is the output. Okay, so you can see 1, 2, 3, 4. There are 4 samples. So input and outputs are separated by 4 samples. In stage 1, in stage 2 it is the 2 sample, and in stage 3 it is the 3 samples. Okay. Similarly, there is a total factor. You can see the ERF, the exponential repeat factor is here 1. It is repeated only once. So 0, 1, 2, 3. Okay. Similarly, it is repeated twice. So in stage 2 it was means it is 0. You can see it is repeated twice. 2 also repeated twice. Okay. But in stage 3 it is repeated 4 times. So this is 0, 0, 0, 0. Okay. So it is 4 times. Okay. So this is how you draw the flow graph of 8-point DI/50. Okay. And you can do the problem if there is a equation is given to you. Okay. So these are the 6 mark, all 6 mark question we have discussed. So these are the references. Okay. So thank you for watching this video. If you have any doubt, you can free to ask me in the comment section. Thank you all.